Ken again, yeah, for inviting me to come here. Actually, this is I visited this building several times, but not in this floor in the Institute of Mathematics. You know, so due to my background, I have some collaboration with the people, yeah, downstairs. Okay, but anyway, so today I will share with you what we are doing, in particular with KAGWA. Okay, I will say something about the KAGWA and the NAOJ, okay, National Astronomical Observatory of Japan, and in particular on the called advanced gravitational wave detector with quantum noise reduction. Okay, before that, I should say something about myself, but I'm not a guy in the astronomy, but I'm only working on quantum artists, so I don't even know what people did with the quantum artists. Okay, so before that, I hope I have a chance to acknowledge my collaborators. In particular, so today I'll share something about NAOJ, ASIAA, KAGWA, and right now there's called a LIGO vehicle KAGWA LVK collaboration, and with something like maybe I will change I can say. Okay, so currently in particular, I have part of my lab is they are doing experiments. Okay, I will say something about it, and some people are working on theoretical part. Okay, so if you are interested, I think we can talk more for some possible collaboration. Yeah. Before that, I don't even know what the photonics is, what we are doing, but very briefly. So in particular, I'm working on optics, I should say optics. Yeah, photonics. So for example, on scattering, so we have some idea to introduce the invisible clock, not only for in the microscopic chip, but also for the quantum effect. Yeah, also the how to control the tsunami. Tsunami by some kind of topological control, with some kind of topological H state. I think if you are interested, I can say something more. Yeah. Okay. So today I'm sorry for the color. So I first of all mention what's the status right now for called the LVK, LIGO vehicle KAGWA, called the global network of gravitational wave telescope or detector. And then I'll mention something what we are doing in Tsinghua on the quantum optics. Okay, in particular, I will say something from the called physics space, the basic idea, and then how to test the quantum mechanics, and how to produce quantum noise squeezing, and quantum state model of the quantum chip, and quantum intense metrology. And I think if time is allowed, I can say something more about our recent work on the achievement of frequency-dependent squeezing at 100 Hz for the gravitational wave detector. Okay, so I suppose you know that there's called a global network of gravitational wave telescope. So there are two in the United States, and one in Italy, and the third one in Kamioka in Japan. Okay, so there's a microscope interferometer. Okay, so that's called LVK, and right now it's a status called O3. Okay, the idea is to have 24 hours, 7 days a week observation to the end of April. Okay. Most likely you extend due to the coronavirus, but anyway, right now. And so the idea is not only to have a signal, but also know the detection and polarization of gravitational wave. So the idea is very simple, like what you use in your daily life. You use a mobile phone about to identify your position. So in particular, it's called GPS. So how many satellites you need to identify your position very precisely? So roughly you need to at least 3 to 4. You need to identify your position, S, Y, D, and synchronize with time, which should be 4. So the idea is not only 3, but also the fourth one. And there's also another called GEO in the Hanover. There's a GEO is called GEO 600, but not 600 kilometers, but 600 meters long. Okay, so this is for testing. Yeah. So right now we are at the stage to have precision detection of gravitational waveform. Not only know the signal, but we want to know how precisely the waveform generated. Okay. So as I say, there are LIGO vehicle and KAGWA. So personally, I am involved in the KAGWA collaboration. Yeah, so I'll say something more about this guy. And last October, actually there's a ceremony, called the LIGO vehicle cargo joint collaboration. As you can see, I was there, but so this is the PI spokesman from Takayashi Kachita. So currently he is the PI for the cargo, and from the LIGO and the vehicle side. Okay, so I don't want to say anything more about this one, but the idea that I mentioned to you is with the help of cargo, we can cover all the sky. Yeah, in particular for the frequency range from a few hundred hertz down to the 10 to the -8 hertz. Yeah. Okay. So this is the target, the frequency band we are looking for. Yeah. So with the cargo, we can have, as I say again, more precise gravitational wave source. Okay, we can localize it or identify the location, and we know more about the parameters of gravitational wave, and then also to hunt the events, and then more idea about this one. So I'll come back to this idea later, because we know, even though in particular I'm working on quantum optics, but until now there's a big problem with quantum optics and gravity. So we hope, in the future we have a chance to know something more about quantum gravity. Okay. Yeah. So in particular, they call the CAGRA as a Kamioka gravitational observatory. Okay, in the Kamioka, actually in the Senkan, in the north part of in Japan. And the difference is this is a 3 kilometer long interferometer underground inside the mountain. But the unique thing is cryogenic. Okay, down to the temperature of 20 Kelvin. Okay. Yeah, so if you like, you can have a look at this called the 2.5 generation of gravitational wave detector. Okay, so I just repeat again. This is inside the mountain, and then cryogenic middle. It takes 1 month to cool down the middle from the room temperature to 20 Kelvin. Okay. So actually, I was there several times. This was a picture, so I suppose you can recognize me. And these are my students. And this is Shinkai-san, the spokesman of Kappa. So if you like, you can try to find out which one is me, who is it. I give you a hint. Of course I'm here. Okay, so there's an info for me. So right now for Kappa, there are more than 110 groups, and more than almost 400 active members. We call them collaborators. In particular, you can see, of course, most of them are Japanese. There's a Japanese interferometer. And in terms of number, I think, Taiwan, in terms of manpower, there are many people in Taiwan, in particular from Tsinghua University. Maybe you know from Uppercom and myself, and I know from the Institute of Physics in Academic Sinica, and Yuki knowing from the National Central University, and Lin Fengli from National Normal University, Taiwan Normal University, and Liu Guojing from Dangang University. Okay, so as you can see, Academic Sinica is also a collaborator for Kappa. Okay, so the organization of Kappa is called the Kappa Scientific Congress. So there's a board. I'm one of the board members. This is my second year term. And as I said, the PI is Kadayaki Kachita-san. And of course, in addition to the board member and then the EO member and the data analysis group, there are many people working on the data analysis. Okay, so I let you know the status. Actually, I supposed to join this LIGO vehicle cargo collaboration meeting next week. I think fortunately. The meeting is cancelled. Fortunately. Okay, anyway, so this actually, I just show you some slides from the Shinkai-san. Okay, the spokesman of KSC board. So as I say again, right now cargo is almost on the final phase to join O3. So there's under the final noise hunting. And the status is, maybe we want to show, actually, the target is 10 mega per second in terms of neutral star distance, but right now the criteria to join O3 is 1 mega per second. And the current status last week is, as you can see, 426 kilo per second. So roughly there's a factor of 2 to overcome. So hopefully we can join O3. As I say, just yesterday, just finished the maintenance. So there should be another noise hunting for another 2 weeks, and then hopefully we can join O3 in the last week of this month. Okay, and the O3 continues to the end of April. So I hope you can hear some good news in the next several weeks. Okay, next month. Okay, so just let you know the status of LIGO vehicle calculator called the scenario. So you know there's called O1, okay, the first observation. There's people detected the gravitational wave detected on the 2015 September 14. Okay, so there's the first one signal of black hole merge, and then very quickly people shut down. I mean the people, the LIGO, they shut down the telescope and do the upgrade and the maintenance, and then for the O2. And the number here is as I said, is in terms of mega per second. So there's a distance of the telescope. And very luckily, vehicle joined O2 only for 1 week, the last week. Okay, they are very lucky to have 2 events in 1 week. Okay, and from the last April 1st, people start the O3. Okay, so O3 is 1 year, continuous 24/7 observation, and right now it's called O3B. And today I think there's some time here, so we hope Kawa can join. And I just let you know until now, for the O3A plus O3B, in the last I think 8 months, we can almost identify more than 60 candidates for gravitational wave. So not only black hole merge, but also neutral star merge, and neutral star black hole. Okay. So there are more events than we expect. And the idea is after O3, okay, of course there should be upgrade, and then O4 and O5. So my contribution is for the future planning, for the upgrade. I would say something more. Of course, you learn there are something called LIGO India. So the idea is to duplicate the interferometer in India right now in Mumbai in the 2025. Okay. So in terms of detector, I just let you know, as I said, it's a binary black hole or binary neutral star. But I'm not the expert on this side. But I will let you know in terms of the interferometer, what kind of the noise we need to take. Okay. So there are some kind. There's an interferometer, so there's a pump laser, so there's a laser noise. Okay. In particular, we use the ND-YAG laser, and the wavelength is 1064. Okay. So we need to reduce the intensity noise, frequency noise. So it's almost the most stable laser we have right now. And then we suffer from the seismic noise, but due to the environment, okay, there's still gas. And so that's the reason why in the interferometer is almost a vacuum. Okay, the pressure is 10 to the minus 5 total. We also have some thermal noise. Okay, the thermal fluctuation, but as you can see, there's a quantum noise, and it means it's an interferometer. So there's a target middle, and then you have a photon number. Okay, hit on the middle, so they call the photon number short noise. Okay, I will explain later what exactly this is. And we also have some kind of called radiation pressure noise. So not only the uncertainty in the photon number, but also the phase. Okay, there's a photon number fluctuation and photon counting fluctuation. Okay, so what I'm going to say or to emphasize today is what is the quantum noise and how to reduce the quantum noise. Okay, so there's a fundamental limiter we need to take. And then how to introduce this kind of quantum noise reduction into the gravitational wave detector. Okay. Yeah, so I just use another spectrum in terms of frequency. So there's a strength sensitivity. So it's lower, it's better. So no matter what kind of the curve you can see, but you can see by the seismic noise, suspension noise due to the suspension system, you have middle, there are some absorption, thermal fluctuation, and quantum. Okay. So the idea is quite simple. So when we say there's an interferometer, no matter there's a 3 kilometer long or 4 kilometer long, so we have a pump laser, and then we have a 2 arm, and then in the output we look at the interference pattern. Okay, so this interference pattern, if this one is modified by the gravitational wave, we can know, okay, there's a signal of the gravitational wave. But as you can see here, this is a detection. This one is empty. But in terms of quantum noise, when we say empty, there's in terms of time. So when I say there's nothing, means in terms of electrical field intensity, it's nothing. So later I use this called phase space. Nothing means not literally nothing, because we know nothing means there are some kind of. So when we say zero, actually it's called expectation value or the mean value. But there are some kind of uncertainty or called standard variation. Okay, so the idea is the vacuum is not empty. So there are always some kind of noise distribution. And so the central idea is can we overcome such kind of vacuum noise by introduce the called squeeze, modify the noise. Okay. Yeah, so actually this is not a new idea. As I say, this is first point out by Kuang Lee, from the caretaker. So almost I think more than 30 years ago. So the idea is in here, as I say again, there's a vacuum fluctuation. So the question in this kind is such kind of radiation pressure fluctuation from quantum mechanically, is either important for the interferometer. As you can see, of course, yes, there's a little point fluctuation. Okay. So the idea is can we overcome this? Okay. So no matter what kind of the sensitivity curve, as I show here, so there are several ways you can enhance the sensitivity. So one thing is increase the power. Okay, so increase the power means you increase the noise to signal to noise ratio, so that you can enhance the sensitivity. Okay, so there are also the future plan to enhance the power. Right now is around the 20 kilowatt, 20 watt, and then to the 100 watt and higher. But if you increase the power, you need to replace the pump laser, and then the thermal noise will also enhance. So there are several things you need to deal with. But the other solution is to use the squeeze. Okay, so with the squeeze, you can easily enhance the sensitivity of the gravitational wave detector. So actually there's a report from the advanced LIGO and advanced vehicle, just last December. So there's a squeezing mode from the gravitational wave detector. Okay. So what we did is, in particular with NLOJ, we not only want to introduce a squeezer into the gravitational wave detector, we want to, the target is, as I said, not at the megahertz region, but at a low frequency, in particular, 100 hertz and 70 hertz. Okay, and one more thing is called frequency dependent. This is what I want to show later, to rotate the angle of squeezing, okay, as a function of frequency. Okay, so as I say, because this is a sensitivity curve which is not uniform. So for example, here you suffer from the called photon number radiation or radiation pressure noise. So you need to squeeze in the amplitude. I will say something more later. But on the other hand, in the higher frequency, you suffer from the phase fluctuation. So you need to do the phase noise squeezing. So we call this called the squeezing ellipse. Okay, there's a change the angle of squeezing as a function of frequency. And then, as you can see, the target frequency is around 100 hertz. So in particular, we apply called a field cavity. Okay, and then in the NAOZ, it's called TAMA, 300 meter long. So the idea is that if you have over the tune of the resonance frequency to 100 hertz, you can rotate the angle of the squeezing. Okay, so recently, last month, we achieved the 100 hertz rotation for the squeezing. Okay, I'll show you something. Yeah. So if you are interested, actually, we can say something more about frequency-dependent squeeze for the gravitational wave. Yeah. So as you can see, there are many people involved here, including two of my postdocs, Dr. Wu Jianling and Dr. Wang Yaoqing. And in particular, this label was, the PI is Matteo Leonati, and Eleonora Capocasa is a postdoc there. And Aditomi is the PhD student from the University of Tokyo, and Zhao Yunhang is a PhD student in the NAOJ. Okay, so actually the story I want to deliver today, we can achieve frequency dependent down to 100 Hz for the gravitational wave detector. Yeah. But before that, I think I can say something more about what we are doing in Tsinghua, in the lab, called the quantum optics in phase space. Okay, so even though I say many things about quantum nodes, and so the question for me actually is what's quantum? I know maybe I suppose you have a different kind of answer. So we learn many things from quantum mechanics, energy quanta, wave function collapse, or called the non-cage locality, shading case, maybe entangled state, EPR pair, non-locality, pairs in equality of steady. So right now there are many things that you can deal with quantum. So as I say, I work on quantum optics. Right now we want to not only for the demonstration in the lab, but also for some application as a quantum technology, including the sensor, simulator, communication, and computers. Yeah. So actually, I start with a very fundamental problem. So for example, when we say, okay, when I teach quantum mechanics or when I learn quantum mechanics, we start with called ASIAA. So what's called ASIAA quantum mechanics? I suppose you should know. We deal with the state, okay, called the Hilbert space, and in some sense, this such kind of state is, too extra or too difficult to understand. So in the lab, we are working on called the quantum state tomography. Okay, so that's what I want to share with you. We can let you know how to make the quantum state precise into the phase space by the direct homodynamic detection. And we also working on some kind of permission system, to ensure the observable to be real. We have a permission operator, but actually right now there are alternative the new quantum theory. We want to extend the traditional permission quantum optics to call the non-permission quantum mechanism. So there's some possibility we can do, and of course we apply the probability, in particular Bond's law or some wave function collapse. And in the lab, we also apply different kind of measurement, in addition to the eigenstate measurement, also called they call Mann-Newman measurement, also called the weak measurement. And the idea is, can we know something more about the decoherence? And of course, there's a time evolution. I think that for you should be familiar with the Big Bang. There's a start of the everything. But for us, we have no idea about the error of time. And in particular, we developed some kind of called the integral history to address this problem. Okay, so I just show you something very quickly. If you are interested, we can talk about. But it's not related to astronomy, but it's very fundamental. So for quantum mechanics, I say we start with the precise. And the question is, can we know something more? Or can we illustrate or demonstrate what's called precise? Okay, so in particular, we can say, okay, we can look at the density matrices. And so that's what we did in the lab. We try to have some kind of called the quantum state tomography, not only to know the precise, but also make the, in particular, this is the vacuum, and then I can show you how to do the squeeze for the vacuum. And just like take a picture of your body, so you know, for example, how good if you want to know something wrong inside, you need to go to the hospital, and then the doctor will take an image, the tomography of your body. So I want to know, okay, if my heart or my liver or something is there something wrong? So it's the same. So if you want to know your quantum state is good or not, is good or bad, you can go to my lab. I can let you know. So this is the idea. In particular, we apply some kind of likelihood estimation. I think that is what people also use in the astronomy. Okay, and recently we apply some kind of machine learning to understand. Okay, in particular, for example, there's a squeeze state, there's a K state, and then how to know what's the state we are. Okay, and another problem we attacked several years ago is called non-emission. So the idea is, when you open the textbook of quantum mechanics, we are talking about the hermeticity. Okay, so H equals to H theta, and but is this true? And there are some challenges to this. Okay, in particular, it's called the non-emission quantum mechanics. So if you like, you can have a look at our paper on the called the reflection on the alternative quantum theory. So I will let you know how to. There are some violation of called the no-scaling principle, or how to think about carefully about the alternative quantum theory. And as I said, there are not only standard von Neumann measurement, there are also some kind of weak measurement. And then if you apply such kind of weak measurement, you can enhance the signal. So recently, actually last year, we say, okay, you can use such kind of weak measurement to say something more. But as I said, it's a very fundamental theory. But if you like, you can say something. So until now, we know quantum is not only, as I said, not only the textbook example. There are some kind of what we call the resource, or called the we can do something with the spooky issue of the entanglement. So if you like, there's related quantum information, but people right now believe that the quantum mechanics is not only you can do in the lab, but you can do something real. So if you like, I can show you small example, but I can skip this. So I just show you one more thing about, for me, actually, I'm always curious about why, even though I'm working in quantum, so what's called quantum, what's called classical, and is there any boundary between quantum and classical? So for example, we look at the current, there's a classical idea, and then what's a quantum current, what's a classical current? Okay, is there a transition or the boundary? Okay, but nevertheless, I use this simple example. Okay, I believe you can have a very simple picture. So in classical mechanics, we know in particular for pendulum. Okay, so there's a simple harmonic oscillator. So we have oscillation of the state of a classical particle, for example, in terms of time. So there's a sinusoidal wave. So this pendulum, for example, is moving from the left-hand side to the right-hand side and come back. But instead, we can use a phase space. So phase space means I use a single point for classical particle, but this trajectory gives us the information about the dynamics or the motion of the classical particle. For example, from the left-hand side, and then move to the right-hand side and come back again. Okay, so for electromagnetic wave or for EM wave, in particular for optics, we are also have such kind of plane wave solution. So we can use this analogy. Okay, so we move to the quantum, and what's called the quantum? So instead of a single point, I need to use a wave function. Okay, because there's a wave mechanism. And then instead of this one, I will use this Gaussian wave function. I will explain later. But the idea is I come back to this one. So this is a harmonic oscillator. So I take a profile of a two-dimensional Gaussian state. Okay, so there's a circle here. Okay, and then this wave packet is moving inside the harmonic oscillator. Okay, so from the left-hand side to the right-hand side. Okay, so I'll just show you again. So there's a quantum version of this phase space. Okay, so from here, and then move to the right-hand side and come back again. So instead, as I say, what I show is, later I will use this one, this circle. This circle. So this circle is a two-dimensional Gaussian wave package in the phase space. Of course, there's S and P. Okay, and then I use this circle to denote the distribution, in particular, full with a half maximum of the wave function. Okay, so it is like very similar like what we know in the classical picture. Okay, so this is called the phase space. So I'll show you again. If you look carefully, there are some error. It means the flow. Okay, we call it quantum flow. But anyway, it's not important at this moment. So this such kind of Gaussian wave package give you the similar idea of classical mechanism. Okay, but there's nothing new, you know. So instead of a point, I use a wave function. Okay, but you know, in particular, I use a Wigner function. Okay, but it's called the probability distribution. So I transfer the wave function into the S and P space. So immediately, what I show is the ground state. But you know, in terms of Wigner function, so we can have a picture of this as a probability distribution due to the quantum wave packaging. But for some special cases, in particular, for example, like this one, n equal to 1, we call the single photon state, which give you the probability, but in the negative value. It's negative. So you know, in classical idea, we don't have, in the classical picture, we don't have any idea about negative probability. So this is the reason we call this called the quasi-probability, because we cannot map the quantum state into the classical state immediately. So there are something, you know, they call it spooky, something very strange. Yeah. So this is the reason we call the quasi-probability distribution. Yeah. Wigner function is not the only one. There are many. Yeah, you can also call the Q function, Boosting function, global function. Okay, the P representation, or in general called the symmetrical transform. Okay, there's a transformation. Okay. Yeah. So in particular, as I say, I'm talking about simple harmonic oscillator, and then there's a coherent state. So that's we know. Yeah. But you know, in terms of eigenstate, called the number state, there are no classical analogy. Okay. So even for the simple harmonic oscillator, and there are one thing I want to emphasize is for the simple harmonic oscillator, there's called the 0 point energy. So the follow number is 0. There's a vacuum, but we have the wave function as a Gaussian. Okay. So this is what I emphasize today for the quantum vacuum, quantum noise. Okay. But there's something more you can do. As I say, in classical state, we say, okay, there's wave function, okay, the wave package. But if we have two, there are two wave packages, but it's not surprising. But in terms of wave function, no. In addition to these two, we should have the superposition. In optics, we call the interference. So interference in between. So actually, there's the same scenario. So we have two wave functions, one in the left, the other one in the right. Okay, so they just move inside the harmonic oscillator, but in between, just the interference. So the interference gives you some kind of superposition. So there's due to the wave function. Actually, it's the idea of shading the K. So if you have 2K, well, actually 1K, one is either alive or dead. So the superposition gives you something strange. Okay. So in the lab we can do this, in particular with the optical setup. Okay. And in addition to 2, you can also have 4. So you know this is called the K state, but for the 4 they call the compass state. So in between you have the interference, okay, interference between 2. But in the center you have the interference among 4, so they call the compass state. Yeah, I don't want to show you anything. So in the lab we can say it's not clear, no, but it's not better. You have a two-way package, okay, interference. But in the center, there's just the interference of the compass state, or the interference from 1, 2, 3, 4, four-way package. Okay. So there's one kind of strange thing you can deal with such kind of shading K. Yeah. But K is not important. The important thing is the interference. So actually we are also working on such kind of information processing with the K. Okay, so I'll go to another step as I mentioned again. So instead of using a single point, I need to use a wave function for quantum state. So I just repeat again. In terms of wave function, it's not the single point in the origin, but there are some kind of distribution. So they call the vacuum is not empty. Okay. So as I just repeat again. For classical, there's a single point. For wave function, there should be a circle. There's some kind of uncertainty, and the size of this circle is defined by the Heisenberg uncertainty principle. So for example, delta S, delta P should be large and equal to h bar over 4. Okay, I remove h bar. Okay, so actually uncertainty relation define the size of the circle. But you can have one step further. I mean, I change the parameter to y, but the product is minimum, or this we call the minimum uncertainty state. But I can play with, for example, delta y1 is, for example, I just take a square, but it's a 1/4 by times a factor exponential minus 2 gamma. So if gamma is smaller, it means this one is, if gamma is positive, okay, so it means this is smaller. But I need to pay the price. The other conjugated, I call it quadrature, or conjugated delta y2 will be modified by exponential plus 2 gamma. So the product is minimum, but on one side is smaller, the other one is bigger. So this is the reason we call the squeeze. So I just show you one more, once again. So if I can prepare a coherent state, a baking, actually it's just a baking, so I don't need to prepare anything. And then I have some kind of, I call it squeeze. Okay, a squeeze means I modify the distribution of the noise distribution for this baking state. So for example, I squeeze from the 45 degree. So this one is smaller, but I need to pay the price because there's an uncertainty ratio. This quadrature or this direction is bigger. Okay, so they call it squeeze state. Okay. So we can modify the uncertainty. So for baking, it's uniform. For example, in here, I can smaller than the baking. So I can take this as an advantage to reduce the quantum noise in the detector. So this is the central idea. Yeah. So actually, it's nothing but the Fourier transform. If you like, we call the Fourier transform. So there's a wave function. So we know the Fourier transform of the Gaussian is also a Gaussian. So Gaussian is a Gaussian. But in one domain, for example, in the time domain, I can narrow down the width of the profile. But I need to pay the price in the other domain is expensive. Yeah. In the limiter, for example, one side is data function, the other one is expensive. Okay. So there are two things we need to pay a price. One, to pay attention. One is we call the degree of squeezing. How strong you can squeeze the noise distribution, called the degree of squeezing. The other one is the angle, squeezing angle. So on which angle, for example, I can squeeze either this way, or for example, from vertical, or from this way or from this way. They call it squeezing angle. So one is the squeezing strength, the other one is the angle. Okay. Yeah. So there are several ways to generate the squeeze state. So I don't want to say anything about this one, but the central idea is that we need to have some kind of non-uniform or non-unitary transform, or actually called nonlinear interaction. So in particular, what I show is this one called the optical pentametric oscillator. So I squeeze it, okay, in particular, for example, in this one, I squeeze it in this direction, in the horizontal direction. Okay. So mathematically, we need to have some kind of nonlinear process. Okay, for example, like a 2-photon process. So I have A delta squared. So if you use this as an operator, actually the squeeze operator is A squared. And then you can easily check if you apply this operator on top of vacuum, then the variance on one side is smaller, on the other side is bigger. But the product is minimal. The product is minimal. So they call the squeeze operator. Okay. So idea is very simple. We need to have, in particular, what we did is 1064, and we need to pump a laser and pump it into an OPO without any input because it's a vacuum, and then there's a squeeze. And the other thing is not only for generation, but you also need to do the detection. And in particular, we apply called the balanced homodynamic detector. We use the same wavelength as a local oscillator. I will explain later. But we want to know what's the fluctuation. Okay, and then we want to cancel out the mean field. Okay, to call the local oscillator. Okay, so if you know me 3 years ago, I'm quite good in the theory. So 3 years ago, I say, okay, we can build up this system. For me, just a main laser, a second harmonic generation for pump laser, OPO, and detection. That's all. But in reality, no, it's amazing. Okay, so by anyway, we try to do that. Okay, from the October of 2016, almost 3 years ago. So there's a new optical table. We ask the worker to dig a hole. You want to know why? We want to reduce or isolate any noise from the power supply. Okay, so this is for the ground, Okay. But anyway, so we have this one. We are lucky. So as I said, it's a pump laser. We have our homemade second harmonic generation OPO. So in the output is a squeezer, and then we have called the more cleaner as a filter for the local oscillator. And my students, they fabricated the circuit for the detector by themselves. I can explain later. Okay, so the first one we have two detectors, two cavities, one for second harmonic generation. So we work with HC Photonics and Longzai Keji inside in Hsinchu. And the second one is PPKTB. Anyway, you know there's a cavity feedback control and the thermal control. And this is another challenge. The challenge one is for the detector. So I just explain again how to measure or how to detect the fluctuation. So the idea is we apply a local oscillator, which is a classical signal, okay, like a Korean state. So for this one, we can define the angle. Okay, so I want to know what's the angle of squeezing. We mix with the either vacuum or the squeezing. But as I said, this is very weak. So this is strong, this is weaker. So we drive the system. Okay. So the idea is that if you want to know this guy, but without this local oscillator, so you need to do the balance, or called the subtraction. So if I have two detectors, they are identical, and then I do the subtraction, I cancel out everything, so there's 0. And the remaining thing is, of course, there's bias. Okay, I can find what I want. Okay, so in terms of theory or mathematically, it's quite simple. You know what's called a subtraction. I put a minus here, okay, and then cancel out everything. So that's all. That's all. Yeah. So I let you know how to do later. Yeah. So in particular, we work with Ping in the Australian National University and Akira Furusawa from the University of Tokyo. So we have our homemade circuit. So how to know this is good or not? So if we have one signal, okay, you have one input. If you have two inputs, we call the common mode. We need to reject. Okay, so they call the common mode rejection ratio. So there's one signal, you have a signal. If there are two, they should be cancelled out. So until now, we can, it's not bad. Okay, more than 84 dB for CMR. Compared to the commercial one, if you are rich, yeah, you can buy from the Newport. So they also provide the balance optical receiver up to 50 dB. Okay, so I think our circuit is good enough. Yeah. So I just show you what's called the squeezing. So this is the angle. I change the phase of the local oscillator. In this picture, I rotate this guy. Okay. So as I say, of course, there's down noise. Okay, no worry about this one. There's down noise, the electronic noise. So when I work at for here, it's roughly almost 100 milliwatt. I drive the system, the signal to here. Okay, so that's called a vacuum. As I said, vacuum, the noise distribution is uniform, so there's nothing changing as a function of the angle. But if I have the squeeze, so you can see I have the signal smaller than vacuum, higher, smaller, higher, smaller, higher. Okay, so as I said, I rotate this one is smaller, and then higher, smaller. So this at this moment we can achieve more than almost 10 dB squeezing. Okay, at 3 megahertz between. But we need to pay the price, as I say, there's no free lunch. So at the same time, there are 20 dB anti-squeezing. We need to suffer. Okay. Yeah. So in terms of spectrum, I think we can achieve squeezing from 1 megahertz to 5 megahertz. So again, this vacuum, and this is squeezing. Yeah, almost 10 dB down to 1 megahertz, and then anti-squeezing. Yeah. Okay. So this is what we did in the lab. So compared to the state of the art that was done in the University of Heisenberg, actually in the Albert Einstein Institute, okay, in Hanover, in Germany, by the Norman Schreiber. So they can achieve 10 dB squeezing. This is the world record at this moment, but it's all the same in the frequency range megahertz between. So as I say again, there's a vacuum, they can down to 15 dB. But in terms of the anti-squeezing, as you can see, they also suffer from 18 or the higher frequency to 24 dB anti-squeezing. Yeah. So I think we can, at this moment, as I said, I only have one optical table, so we estimate all the parameters we have. So we think we can, can go more than 10 dB squeezing. Okay, so I'll just show you again. At this moment, the pump power is around 100 milliwatt. So there's a 10 dB squeezing, minus 10, and 20 dB anti-squeezing. Theoretically, we can achieve it here, but we know there are some problems we need to address, in particular the face noise of the cavity. Yeah. So we are also working on this guy. Yeah, so there's a label I have. I think all of you are welcome to have a visit. So as I said, there's a pump laser, there's a second harmonic generation, there's an OPO, there's a more cleaner, there's a detector, and as you can see, there's another squeezer. So actually, we are working on 2 more squeezers to have the squeeze kit. Okay, this is for the entanglement. Yeah. At the same time, we have one project to go beyond the label, from the optical table to the chip. Okay, so we work with Professor Chen Yanhong from National Central University. So they have the facility to fabricate the periodic pole in Nishinaya Bay. So we want to have such kind of squeezer on the chip. So we have already have some design, and then they are fabricating the chip at this moment. So I hope I can be something later. Yeah. So at the same time, as I said, not only the source, but we also working with Professor Li Yisan from Central University on the called the single photon avalanche diode. Okay, so called the SPAD, and then with some kind of gating, they can we want to combine this together. Yeah. Okay, so I think the performance is good, but we wanted to on the chip level. Okay, and then we can have a portable device, for the detector. Okay, I can skip this one. So actually, we also work on some quantum information processing, for example, the control NOT. So actually, there's called the CNOT gate on the chip. So we have a source, we have a detector, and then with the chip, we can do some kind of function, some kind of control NOT or gate operation. Yeah. We also approach some people to have a cone, and the idea is can we use such kind of the quantum source, not only for the gravitational-wave detector, but also for the daily life, in particular, for example, for the distance measurement, like a laser tracker. Okay, so in general, we call it quantum enhancement metrology to enhance the sensitivity of all the interparameter base. So interparameter can be very large, like gravitational-wave data, or in a very small scale. Yeah, I don't want to say it, but actually we also apply some kind of machine learning, we call the quantum machine learning. I know many of the people here are working with the machine learning to find the signal. So if you are interested, you can join us actually in April. So there will be Dr. Alexei Minakov. So currently he's a postdoc in the University of Basel from Switzerland. So he will give a lecture, a series of lectures on the quantum machine learning. So you want to know learning for quantum. Yeah. Okay. So I think in the next 5 minutes I will finish this. Okay. So this is the state of art. So even though I'm working in quantum, so what's wrong with quantum? There are many things we don't know. So to be honest, I should say, until now there are still many trouble with quantum mechanics. It's not very old. For example, there's like Steven Weinberger, he have 3 books on the quantum field theory. Actually, there's an article, 2 years ago. The problem with quantum physics, how it's made. The quantum physics does not apply to human. And actually, more recently, I take this one, if you can see, from the New York Times, So there's I'll show you. There's the article, opinion by the Shin Carlo. Actually, he is a professor in the physics. So he said, okay, even physicists, I believe I am a physicist. okay, don't understand quantum mechanics. I agree with him. Okay, the worst, actually the worst. Yeah, these physicists, including you, yeah, don't want to understand it. So it's not a joke. Actually, until now, even though there are many theories, but we have no idea about this guy. Yeah. To be honest, I don't have any concrete idea. But with the gravitational wave telescope or the signal, I believe we can understand gravitational wave, or in particular black hole, yeah, in a better and better way. So maybe at some stage, yeah, for the future plan, there are also some agenda to test the quantum gravity or for the graviton, but not in the near future. But for the young people, I believe they should be. I hope I should be alive at that time to know the unifier of quantum gravity. Okay, so. But instead, actually, no, I'm working on quantum optics. Actually, we learn many things from the astronomy. So in particular, in the lab, we use such kind of, we call the HPT, Henry, Brown, and Twist interferometer. So this is the idea, if there is one single photon, if you have coincidence counted on two detectors, you only have one photon. So coincidence means you have a tip called the second order correlation function. So that's the metrology we use in the lab to know the property of a single photon. But if you come back to this one, actually there was a test of new type of stellar interferometry. Serious. So no, we borrow the idea from the astronomy. Yeah. So for me, it's the same. You use a telescope to look in the galaxy. So the signal is very, very weak. Okay. So we in the lab we look at the vacuum. Actually, there's almost nothing. Yeah, so for me, so that's the reason why I'm happy to join them. So I just repeat again what we are doing in the NAOJ, so I don't want to say this guy. So the idea is this one. And so as I say again, there are two things you need to pay attention for the squeeze state. One is the degree of squeezing, how strong you can squeeze. The other one, the angle. So for the first one, how strong you can do, according to the advanced dipole parameter, so as I said, the neutral star range. Okay, the bigger is better. So you can see there's in terms of squeezing. When you look at this one, okay, the blue one, with a lower power, okay, so there's a 10 dB is better. Actually, it's the best. Of course, you can increase the power, as I say, from 25 watt to 125. Okay, you can look further because the signal to noise ratio is enhanced. But as I say, they are not only squeezing, but also anti-squeezing. So there are some compromise, or you need to work on some sweet spot. So as I show you, in the lab, we have 10 dB squeezing. So we are lucky, we can do this. Okay, and as you can see, there are two curves here. One is with FC, called field cavity. The other one is without. Okay, and the other thing, as I mentioned to you, actually, in the lab, we have squeezed in the megahertz range. But for the gravitational wave, we need to work on the lower frequency. In particular, for example, for carbon, it's 100 hertz. And how to shift the frequency to 100 hertz? You need to apply field cavity called FC. Okay, so I can skip everything. So as I say, with this one, you can change the angle by detuning of the resonance frequency. So from the called frequency dependent squeezing. I skip everything. So there's as I mentioned, I talked to Ken, but actually in the Mitaka, so there's a NAOJ. So actually there's a 300 meter long called Tama. Tama. It's not a dirty word, but anyway, it's Tama. Anyway, yeah, so there's a Tama 300, okay? So we actually, there are several great progress. Actually, we are lucky. Actually, we work with them from the July 2018, and then very quickly from the kilohertz region. Okay, 2 months ago is 1 kilohertz, but last month is 100 hertz. Okay, so yeah, I just show you something. It's a little complicated, yeah, but I think, yeah, of course we need to deal with the loss and phase. I don't want to say. I just show you the last one. Yeah, so this is what we have. Actually, we submit the paper already, so we can, this is squeezing, and then rotate the angle to anti-squeezing, or on the other hand, anti-squeezing, and then rotate it to squeezing. Okay, so this is called a dependent. I think there's a first demonstration on the frequency dependent squeezing in the world in the 100 Hz. Yeah, so if you like, you can, if you like, I can give you the preprint on this paper. Okay. So roughly that's all. Yeah. So there's the people who are working. As I said, there's Zhao Yuhan, last year PhD student. Aditomi is a second year PhD student in the University of Tokyo. This is one of my former master student. Unfortunately, she went to the industry company to make money. But anyway, there's a Idenora, Kapokasa, the postdoc in the also there's a Dr. Ujemi, in there. So again, there's another. So typically, my student and my postdoc they will visit there, for 3 months, in the first half of the year and the second half of the year. Yeah. So I end with my talk with this. So actually, we start with everything by looking in the sky. Okay, so in the very beginning, we use our naked eye, and then there's a Galileo Galilei, so who is a telescope. And even though I'm working, I believe I'm an optical guy. Either in my name, in my name is Kuang Lee. Okay, actually my English name was some kind of anyway. So, but right now we are at the stage with a quantum telescope. Okay, with a noise reduction. So I just summarize what we did. So I show you we have the 10 dB squeezing, and we also have the superconducting nanowire to enhance the sensitivity. So this is something maybe we can focus with the Dr. one here. And so this is supported by our quantum center. And we are in particular working in the lab on the metrology for the state tomography and with some kind of machine learning processing for quantum information processing, and it's called the squeezing gate or gate operation. So we are supported by Marshall Foundation for Basic Science, US Navy, okay, with overseas grant. At the same time, we also have another 5-year project for the squeezer on a device. Okay. But not from the division of physics, but from the division of engineering. The division of engineering. Of course, we have some project with ASIAA, University of Tokyo, and Max and JSPS on the frequency density. Okay, so roughly that's all. I hope you can enjoy. Yeah. So thank you for your attention. Thank you very much.
Any question? Horrible.
So if 10 dB is optimal for the current setting,
Yeah,
what's the perspective? As you say, you want to work on the future detector. So
okay. So right now, okay. So for the future plan, there are several strategy. Okay, one is apply the squeezer 10 dB. The other is to use a high power laser to increase the power, and then another one is use a big needle. Okay, right now but it's a big issue, and people also think about to replace the wavelengths from 1064 nanometer to 1550 or higher or longer wavelengths. Okay, so it depends on the parameter. And then I didn't mention anything about the alternative solution. Maybe last week people in Australia they use the entangled light source, EP bar pair. Okay, so there's another alternative solution. Okay, so until now we are talking about just use the single wave or single particle wave function. So I manipulate on the single particle wave function. But if we have two, okay, like an EPR pair, there's another degree of freedom. Okay, and so until now, this is what I know. Maybe there's a Einstein telescope. Yeah, actually, so there are also some strategy or some approach. Instead of using the filter cavity, by using called the speedometer, different kind of approach to do that. Yeah. So, but this is what we can see for, as I say, what we can see until 2025. For after 2025 or 2030, I think people will go to the space. So, it's a totally different story. Yeah. Like Lisa, like another story. Yeah.
Thank you. Any other questions? Okay.
Maybe I can give a short comment. So what people did in this moment, for example, what we show in the frequency dependent squeezing, we only injected about 6 dB. Okay, and in LIGO in the vehicle right now it's almost the same, 6 dB. So there's still a long way to go with 10 dB squeezing. Okay.
So I think audience here might be more interested about the use of this technique. Can you say in your last few slides on quantum telescope? We don't really know what you mean by quantum telescope.
Okay.
And how about super resolution?
Yeah. Okay. So here I say quantum means but actually there's a case called interferometer, but we reduce the quantum noise. Okay. And of course there are some kind of proposal, what they call the quantum enhanced interferometer. Okay. So enhanced means as I say, but it's not only for telescope, but I can show you something, like this one. So quantum enhanced metrology. So until now, I think all the metrology, including precision measurement, telescope, people apply only the laser light source. For me, laser is a classical light source. Okay, classical means the output is a coherent state. So can you replace such kind of light source by the quantum light source? This is what I mean. Okay, but at this moment, we don't replace the laser source. We only replace the detector. Okay, so this should be another solution. And then there are some idea or proposal using called quantum imaging or quantum interferometer, or on the other hand, called quantum enhanced technology.
Thank you.
Yeah, maybe I missed. You squeeze the noise.
Yeah.
What kind of price you pay?
Yeah, the price is anti-squeezing. So that's what I say. There's no free lunch, but it's allowed to. Yeah. So. Oh, there. Okay. So here, as I say, the price is paid. The price I pay is. I can show this guy. I think it is more easy for this. Yeah, this one. So that's the fluctuation of a coherent state. So it means in terms of phase, or in terms of time, okay, it's the same. Omega t is the phase. I can do the measurement all the time with the same level or the budget of noise. But in terms of squeezing, I can only work at this moment. And then for this period, or for this range of phase, the noise is bigger. Okay. So of course there is no free range, Yeah. So in terms of sampling rate, there's a reduction in the sampling rate. So, okay, I do the squeeze, so I need to do the measurement on this moment, and then I squeeze it. I get it off this guy. Yeah. But it's the same for all the. And I have to say, almost all the this one called quantum enhanced technology, like a single photon. If we know the single photon, we do the measurement. If there is no single photon, of course there are fluctuations. Yeah, you get rid of this. Yeah. So there are some trade-off for looking.
Okay.
So you mentioned about the squeezing, but in the lab, how exactly do you do the squeezing? Do you apply certain field or something?
No. So in the lab, as I say,
it's only the optical paths that you
use. Yeah. So, but it's a simple cartoon. So in fact, we need to control everything. It's more complicated. But okay, so the idea is it's quite simple. We just apply the OPO. Okay, and then I think the question is how to, by changing the pumping power, we know there's different kind of different degree of squeezing. Okay, as I mentioned here, like this one. Okay, so the degree of squeezing can be controlled by the pumping pump. Okay, and then there's another degree of freedom called the phase. We need to lock the phase of the, so there's some kind of injection you need to do. Yeah, so it's not totally easy as I say, but roughly say you need to control and then have some kind of feedback of everything. Because what we want to do is we want to measure the quantum fluctuation. So it means we need to get off all the uncertainty of the cavity of the feedback of it. So it's the same for the gravitational wave detector. As I say, if people can overcome all the fluctuation from the seismic noise, from the suspension noise, and from the thermal noise, okay, only at that stage is the time to apply the quantum noise reduction. Otherwise, there's a dominant noise will be the classical noise.
Good. Any other final question? So if not, let's say straight on again.
Okay.